All right, so this is about where I finished up in class today, where we were looking at the reactions of nucleophiles with alkyl halides to form new nucleophile carbon bonds. And I finished up pretty much so at this slide, I think, where I was showing you that these types of simple reactions can actually be used to make very important things. So, for example, ethane butol, which I believe is an inhaler for people with lung issues. And then, of course, Prozac. The first step in making Prozac is to react this alkyl halide with this so-called methylamine to form a new carbon-nitrogen bond. And then, of course, there are other steps that go into making Prozac, but this is the key reaction here. And these are reactions that you all learn in Organic 251. So these do play a role in a variety of things medically and in other areas. They even play a role biologically. So biological systems need to make molecules all the time. Even the human body, we make molecules all the time. We are really organic chemistry reaction plants, if you will, in some way. But the thing is that we don't actually have alkyl halides floating around in our bloodstream. At least we shouldn't have alkyl halides floating around in our bloodstream. But our body actually has this molecule called SAM, which stands for S-adenosyl methionine. Now, it looks like a complicated molecule. Don't worry about it too much. This is the business end. It's just a simple methyl group attached to this positively charged sulfur. And so this whole group that I'm circling here, okay, this part right here, you can think of it as a biological halide. Okay, it has the reactivity similar to bromine, and we know that bromine's a good leaving group, and so is this. This reacts about the same as bromine. You can abbreviate this, shown here, as CH3-SR2 with the positive charge on sulfur. So one of the R groups, of course, would be this piece, and the other R group would be this piece. Okay, but what you need to do is you need to think of this as the biological equivalent of bromomethane or methyl bromide. Okay. Now, in a number of biological processes, some nucleophile will react with SAM to put a methyl group on that nucleophile. So you make a methyl group nucleophile bond, and SR2 functions as the leaving group. So you can think of this as the halogen. You can think of it as the bromide or the iodide, okay? And you end up with a substitution product. Now, when you get into biochemistry, they will call this process methylation. And it turns out methylation is an important biological process, as I mentioned. And it's important in a number of areas, but one in particular, and that is the fight or flight response. So you all may have been in this situation. I hope not, but if you've ever been in a situation where you get scared or you get stressed and you feel like you're under danger, your body starts to produce a lot of adrenaline. And that adrenaline, of course, increases your heart rate, increases your blood pressure, gives you a dilation of your lungs, lets more air in. People who are under fight or flight response have reported being able to run distances that they normally wouldn't be able to run. We've got reports of people being able to lift heavy objects that they normally wouldn't be able to lift, etc. And that's all because of this extra adrenaline that is going around in your bloodstream and doing what it does. Now, as you can imagine, you don't want adrenaline floating around in your body all the time, right? High elevated levels put you in this fight or flight. Your heart rate goes up. If you were in this all of the time, it would kill you prematurely, right? But you need it. It's a defense mechanism. We do need fight or flight. So what happens is your brain, when it senses stress or danger, sends a nerve impulse to the so-called adrenal gland through some nerve process that I'm unclear of. But once the adrenal gland gets the signal, noradrenaline will react with SAM to make a carbon, or a methyl group I should say, but carbon-nitrogen bond, and that makes adrenaline. So you go from noradrenaline, which does not increase these things, to adrenaline, which all of a sudden increases these things, and you're in fight or flight. And so once you get out of that situation of stress or danger, the signal goes away, the synthesis of adrenaline stops, and you return to a normal biological state, if you will. Okay. This is nothing more than an SN2 reaction. Noradrenaline reacts with SAM to make a new carbon-nitrogen bond, and we call that adrenaline. But it's a simple SN2 reaction that occurs to make the adrenaline when you need it. And so all of that was about SN2 reactions. Okay. Now, if you'll think back to what we talked about today in terms of SN2 reactions, we learned that the rate of an SN2 reaction is proportional to the concentration of the nucleophile and the alkyl halide. Both of them are involved in the rate determining step. In the SN1 mechanism, only the alkyl halide is involved. And so the mechanism for the SN1 reaction is shown here. So the alkyl halide, the halide has to leave first. And as you can imagine, this should be a very slow step because you're getting to a carbocation that doesn't have an octet. That's going to be unstable, right? So it's going to be high in energy. And so you get the carbocation in the first slow step, and in the second step, some nucleophile, in this case, my slides show acetate functioning as the nucleophile. This oxygen with the negative charge attacks the carbocation, and you form a new bond between the oxygen and the carbon shown here. The rate of this reaction is only dependent on the alkyl halide concentration, this thing. You can add more acetate all you want. The reaction doesn't speed up. Okay, it depends on the concentration of this. That's why it's called SN1. Substitution, nucleophilic, unimolecular. One thing, right? And so an SN2 reaction requires two things to be involved. That's why it's called bimolecular. And an SN1 reaction requires one thing in the rate determining step. That's why it's called unimolecular. Okay? Now the mechanism for this, if you draw it out in an energy diagram, we've talked about energy diagrams before. This looks very similar to the energy diagram we saw in the addition of things across carbon-carbon double bonds, right? And that's because the addition of things across carbon-carbon double bonds, like HX or water with sulfuric acid, went through a carbocation intermediate. Well, these go through a carbocation intermediate too. So this is the rate determining step because it's got the largest energy of activation. You can see that the line here is much larger than the energy of activation in the second step. And so what's happening is this carbon-halogen bond, the carbon-bromine bond, is breaking. Notice the halogen is taking on a partial negative charge because it's pulling the electrons to itself. And the carbon's getting a partial positive charge, right? And so this is the slow step. You end up with the carbocation intermediate. Then the nucleophile attacks that carbocation to form the second transition state where the nucleophile is approaching the carbocation. And that doesn't take as much energy because everything now has an octet. The energy is going to be lower, and you're going to form product. So interestingly enough, an SN1 reaction has two steps. Step 1, formation of the carbocation. Step 2, nucleophile reacting with the carbocation. An SN2 reaction only had one step. The nucleophile is attacking the carbon as the halogen leaving group is leaving. It all happens in one step. So SN2 has one step. SN1 has two steps. So don't get those confused. Make sure you understand that clearly. It will most likely be on the exam. Okay? So in an SN1 reaction, we're going through a carbocation, and we learned in Chapter 5 that carbocations aren't all of equal stability. Right? We know that a tertiary carbocation is more stable than a secondary carbocation. We also know that primary carbocations are very hard to form, and methyl carbocations are impossible to form for all practical purposes. Okay, so this is an example where we have a tertiary carbocation. Notice we've got 3 methyl groups around the central carbon. So these sticks represent sp2 orbitals. And then you see the vacant p orbital. There's no electrons in this p orbital. That's why it has a positive charge. Okay, and what you'll notice is the orbital is both above and below the plane of all 4 of these carbons. So all 4 of these carbons are lying in the plane, and the p orbital goes above and below. So you can imagine the nucleophile attacking from the top or the bottom. The whole orbital is positively charged, not just the blue part. Don't get confused by that. So the nucleophile could either approach from the top and make a bond, or it can approach from the bottom and make a bond. And this has an important consequence. So if we took a chiral tertiary alkyl halide, in this case bromide, right? So this is a tertiary alkyl halide because this carbon is bound to 3 other carbons, and all of them are different. We have a methyl group. We have a methyl group that has a deuterium on it, so that's clearly different than this. And we have an ethyl group. So we have 3 different carbons here, and we have bromine. So there are 4 different things attached to this carbon, which makes it chiral, right? And if we take 1 enantiomer of this and we react it with some type of nucleophile, right, this will undergo an SN1 reaction. So the leaving group leaves, and you end up with the planar carbocation. Now our nucleophile can either attack from the right side or the left side. Okay, if it attacks from the left side, the nucleophile would come in here and you'd make the nucleophile carbon bond, and it would push these groups over to this side of the molecule in the tetrahedral arrangement around this sp3 hybridized carbon. And you would end up with this enantiomer. If, however, it attacks from the right side, you would make the nucleophile carbon bond on this side, shown here, and it would push these groups to the other side when it makes the tetrahedral carbon, okay, because it's sp3 hybridized. These 2 things are enantiomers of one another. They are non-superimposable mirror images. And so what you would find if you did this reaction, right, so this molecule would rotate plane polarized light because it's 1 enantiomer, but the product would no longer rotate plane polarized light because it's a 50-50 mixture of both enantiomers. So it is a racemic mixture, and we would say that this reaction undergoes what's called racemization. So we just took a very expensive starting material and made a very cheap product. Racemic mixtures are cheap to make. Chiral and optically pure materials or optically active materials are expensive to make, and so this would not be a good thing to do if you were working for a company. So knowing how these reactions occur, of course, is quite important. All right, so we're going to stop there for today. So I finished up what I should have covered today. And Monday we went a little longer in our group work than I thought. I'm going to be traveling to a conference on Wednesday, so I won't be in class. My graduate student will be there. I'm giving him an in-class assignment for you all to work on, so you'll be able to work on that in groups. So it's very important for you to be there on Wednesday. Also, it is important for you to be there on Wednesday because you have to turn in quiz for Chapter 6. So make sure you have all of your homework ready to do. He's only going to give you the last 3 minutes of class to do Chapter 6, okay, and or to turn in the problem that I assigned for the quiz for Chapter 6. So make sure you're there and ready to turn that in to him at the end of the day. Okay, so you might ask, well, what's this going to do to our schedule? It will bump our schedule. So what we were originally scheduled to talk about on Wednesday, we will move to Monday, and we will make up that time as we go on, as we have opportunities to do so. So don't worry about it. Wherever we get to before the next exam is where we get to, and that's what I'll examine you on. So we are going to be delayed by a day in the syllabus until we can get caught back up. And I'll try to get caught back up over the next couple of weeks. But keep that in mind, and I will see you all next Monday. So next Monday, we will be doing what we would have been doing on Wednesday in the syllabus. So keep that in mind. Come prepared next Monday, having read all the material, and we'll finish up Chapter 7 next Monday. But this Wednesday, when you go to class, in-class group work and a quiz. Have a great time, and I'll see you all next week.